Okay. Um, Up to today, what we talk about in the bending, when we were talking about the bending, it was like everything was around the um, symmetric axis. Basically, we thought everything is symmetrical, it's bending symmetrical about for example, all the problem you had about the horizontal axis, or it could be about the vertical axis. So I want to very quickly draw a shape to show you what it means that, okay, if I had a beam to look like this, and back, something like that. So if I put the axis on that, so it says x, y, z axis, it's moved, it's going this way, so as if this is centroid, so that's the x going this way, and the y going up, and the z going this way. So if we had this, so far all the bending we were talking about was, in this case, was about the z-axis, for example. So it was about that z-axis. So if I, for example, I want to put and vector there, it was look like, I'm trying to show, so it was extend that. If I, this is my z-axis. This was about, was a bending about the z-axis. So that was what we had up to this point. So it says m about z. So if I draw it from the front, it would look like this. If the cross section we have. And then, okay, assume this is the centroid here. So if I have my centroid here, I have the z-axis and y, so that's going to be the y, and I have the z, and then I have the moment about that. Z-axis going like this. So there's the z-axis is going to, I want to show the moment. That was the moment vector. That's going like this, just bending like that, about the z-axis. So that's what we had up to here. So it's bending about the z-axis in that case, and it's going to bend there. So it's a symmetrical bending about that as it's going, it's bending symmetrically. But what if the m is not about either of the z, x, or y? It's about an just imaginary axis that's not about either of these three axes. Then what would happen? So that's the case that we want to look at. So let me draw that again. So for example, I'm going to redraw that. So if I have my cross section look like this. And again, centroid point here. So if I go ahead and put the the x and y z axis, so again assume the c is there. And then I have the x-axis coming like, so that's the x, and the z going like this, and the y going up. And that's it. Same. Now if I go ahead and say, hey, you know what if there's an axis that is not either of the x, y, or z? I have another axis that's gonna bend about that axis to see what happened here. So let's see what axis. So assume the axis that I'm having the bending about that is gonna be the blue. So some imaginary axis going like this from here, for example. Some imaginary axis like this. So assume it's I have a moment about that axis, and it's going to be bending about that axis, so it's going to bend. It's bending upwards, so it's going to be and about that. So if this is so it's bending about that blue axis. It's not about the x, not about the y, it's not about z, about that blue axis. So I'm going to draw it from the front so you can see it a little bit better. So if I have that cross section, draw it from the front, that will look like this. Then we have the centroid here, and then we have the z-axis, we have the y-axis, and then we have that new axis that's going, assume it's going like this here. So that's my axis there. If, for example, I'm going to call it AA, assume that's the A. And then I have the moment about that AA, which will be like this. So that's going to be the moment here. That's the M. That's bending like this. So that's the if I look at it from front, that's what I'm gonna see. So now if I have something like that, how I'm gonna work with that? How can I work with the case? Look it like that. If we have it like this, that's gonna be on the axis, that's not y or z, because it was about the z, that's easy. About the y, that's easy. We had it before. But what if it's not about any of them? If you had a case like that, we have to go ahead and find a component of that moment about the z and y. So basically, we are gonna see what would the component about either of those axes, and then work with it. So in that case, I'm gonna have two components. One of them is gonna be about the z-axis. So I'm gonna have the m about the z with going this way. I'm gonna have the m about the y, which will bend like So I'm gonna have these two. So basically, I'm gonna again, this is the centroid. So I'm gonna find the component of that on either of the z and m, and then I'm gonna say, hey, this is gonna be equal into two cases. So I'm gonna have it once about the z-axis and once about the y-axis. So it's basically two cases. So if I break it down into two cases, it's gonna be, if I draw that, it's gonna be two cross section. So that's gonna be one. Plus another one. And then if, again, I have the centroid, the y, z, and the centroid, and y. Then once I have it about the z, and once you have it about the y. So once I have it, I'm going like this, m about the z, and then once I have it, m going up, or about the y. Like that. So I have to calculate the stress once about the m about the z, and once about the m about the y, and then add them together. So in this case, if I, for example, if you look at what we have here about the z, so I can go ahead and say, okay, the sigma x would be negative m y I about the z, and then it's going to be plus the sigma x would be, for the other one, plus m y z I about the y. And then so I add these together, it gives me the total shear stress. So in general case, so it's one case, in general form, what I would have is that I have to resolve the moment about the axis, go ahead and find the sigma x about either of the axes, and then depend on if they're positive or negative, add them together. So I can say that in general case, the sigma about the x is plus minus depend on which direction there's, so it's going to be m about z, y, I about z. Again, plus minus depend on the direction of the moment, m about y, z, I about y. So it's a general formula that we can use to find, and so the direction depends on, because we assume the moment is there, so it could be the other way, so then the sign of them will change. And in this case. So that's how we resolve it when we have it. Remember that in that case, if we want to find a neutral axis, so then we have to, well, to find where that sigma x becomes 0. So that neutral axis is not going to be on the A, it's not going to be on the Y, it's not going to be on the Z, it's going to be somewhere between them. So usually it's between the vector M and the principal axis. So I don't know if I can show it if we consider that angle as a theta. This is angle. Yeah. If we consider that angle as a theta, and then there would be and this is going to be the neutral axis, and that angle with the neutral axis would be phi. Then phi would be the tangent phi. Would be IZ divided by I y tangent theta. So again, as you see, the neutral axis is not gonna in either of the AA or Z or Y. It's gonna be somewhere between the. Remember that the neutral axis is located between vector. I'm gonna write it here. Neutral axis is located between vector M and principal axis corresponding to minimum moment of inertia. So for example, in this case, the minimum moment of inertia is about the y, so the neutral axis is going to be between M and y. If the minimum moment of inertia was about z, the neutral axis was between the axis and the z. So this is the case that if we have the moment that's unsymmetrical, that's not about either of the axes. The next one is that, okay, so this is unsymmetrical, that's gonna be look like this. And now what, so this, now the next we want to look at the general case of the eccentric load. Remember that initially we look at the eccentric loads. What if we have a moment and the axial forces on the cross section? Then it says that, okay, what if the moment is not about the x or about the y or z axis? Now we want to put these together. What if the moment is not about either of the z or y axis, and at the same time we have the axial load? I'm just going to give you I'm not going to go into detail, I'm just going to give you how we approach those kinds of problems. So the next is the general eccentric axial load. So basically what it says in this case is that your moment is not about either of x or y axis, and you have the central, the axial load as well. So in this case, let's look at a very simple example. Assume I have a cross section like this. I have cross section like this, and then I have the axis going through the centroid. Okay, this is the centroid, and then I have the, similar to that, I have the x going out. So that's the x. I have the y going up, and then I have the z going this way. And this is my centroid. And then in this case, I'm gonna have a load that is, assume so I have the load P is applying here. The axial load applying at that point there. Assume the case, I have a load applying there. So if I have a load applying there, let me extend my axis. So that's the y. So if I have applying load in that case, I want to work with that. The only way I can work with that is that I have to bring that load to the centroid. I cannot work with that when the load is off the centroid if I want to find the axial forces. So I need to push or basically move the load to the centroid. So that's what I need to do. So I was said, okay, I'm going to have this equal to, I'm going to have the same cross section. So I draw it as the cross section as rectangle, but it doesn't matter whatever shape it has, that thing should go through the centroid. Similar to here, that everything that's the centroid, the axes are the centroids are the same. So it should go through the centroid. And then again, I'm going to have my x-axis come out. And I'm going to have the y-axis going up. And then I have the z-axis cross section. Now, if I want to bring that P to the center, I go ahead and say, hey, I will bring that P from there to the center, so that we extend the X. So it's going to be along the X at the centroid. So that's going to be the force P. That's the P. I put it to the centroid again. That's the centroid. Now that I move that P to the centroid, what happened is that, remember from the study, if we move the force, we are going to unbalance the moment. Either we are generating more moment or less moment. So, for example, if I have the force here and take the moment about the point that the force is applied to, the moment is zero because the force going to that moment. Now that I move the force there and I take the moment about the previous location of the force, now that force has the moment about that. So these two are not equal because previously there was no moment about this point here. Now there is a moment about that point there. So I have to get rid of the moment I created by moving that. To get rid of that, I have to balance the moment. So whatever moment I created by moving it from here to here, I have to put the opposite of that on the section to balance the moment I just created. So one more time. The P doesn't have any moment about the point here. Now about the same point, P has the moment. So I have to put the counterbalance moment to balance the moment I just created by moving the P to that point. So that case, what I'm gonna make that I'm gonna make two moments here. So one of them is gonna be, so one of them is M about the Z, and one of them is about the Y, and one of them is gonna be M about the Z. So it's gonna be M about the Y, and then it's gonna be M about the Z. And if I want to find them, it's very simple. The moment that I created is that if this distance here is, call it, for example, D along the Y, so it's D about the Y, and this distance is here is D about the Z. So the moment about the Z the P times the distance. So it's going to P times dy. And M about the Y is the P times dz. Just that distance. That's what it created. So if you look at it, it creates a moment about the Y like that, and it creates a moment about the what is Z like this. So now I have the case like that. So if I move that and then I put the effect of the basically whatever moment effect it has there on the centroid. Now I have everything about the axis. So now I can start to move toward with that. So if I have that, in general case, again, it's simple case, but in general case, the sigma would be plus minus P divided by area. Again, depends on the direction of the P, because right is tension. If it was compression, so it would be negative. Plus minus M about the Z times Y divided by I about the Z. And again, plus minus M about the Y, Z, I about the Y. So, as I said, here is the P here. If I move the P in other location, that can become plus minus. It becomes, for example, it's the tension. Right now it would be plus. If it's a compression force, so it would be minus. So that plus and minus we have to decide about it, depending on where the force is located. So, again, quickly recap that is that if the force is not at the centroid, you have to move the force at the centroid. So I move the force to the centroid. When I move the force at the centroid, the moment the force that has here is not the same as I move the force there. So look at here, the force here has a moment about the Z like that, and has a moment about the Y like that. So I want to bend it that way about the Y, and that way about this. When I move them to that point, to the C, those moments about the Y and Z would be disappeared. So I have to go ahead and add those moments, so make sure this is behave exactly the same way. So I move the force to the centroid, and then whatever moment this force causing about the Z at its original place, I will add it on the Z. Whatever moment it causes about the Y when it was at its original place, I will add it about the Y. So now these force and these two moments behave exactly the same way as this force doing it here. And now that I have them here, I calculate the stress from each of them. So I calculate the stress from the force, I calculate the stress from the moment about the Z, I calculate the moment about the Y. And as I said, depending on the direction of the moment or the force, then I have this, and the sign you will just find it from there. There. So the plus and minus sign will be defined by location of the force and moment. So plus and minus signs are defined by direction of the force and moment. And the last thing is that, so where would be the neutral axis? Again, the neutral axis is where that the sigma is 0. So on the line of neutral axis, we know that on the line of neutral axis, we know that the sigma x is 0. Therefore, to find the line of neutral axis, so neutral axis line would be when the sigma is 0, or basically when we have that equation is 0. So I have the plus minus PA plus minus MZY divided by IZ plus minus MYZ divided by IZ would be 0. So basically set that 0, and this is the line of the neutral axis. So that's where your neutral axis is located. The same things here. Remember that the same things here if you want to find the neutral axis for the previous case. Yeah. This is where the sigma is 0. So you can find it there. So these are the last topics we are covering in the bending, the pure bending. And then next we are going to look at it, how we can use this knowledge to design a beam. So the next step is that we want to put this knowledge that we have about this pure bending that we had here, in case of that, and see, okay, how we can use that to design a beam. So up to this point, okay, we know these are the equations, we know how to find the stress, we know how to find the strain, we know how the deformation is there, we know where is the neutral axis located, but now how we can use them to design a beam. So before we get to that point, we are going to start looking some information from the statics part mostly. So this is the reviewer reviewing from the statics, and then we'll look at how we want to work. So the next step is that, okay, how to design a beam. So want to see how we can do it. The very first information is, again, I said, in this case, I'm gonna go do some review, the book do some reviews about the beams, the types of the beams first, and some reviews from the shear calculation, moment calculation from statics, and then we get to point at how we will use this information to design it. So first of all, the type of the bending that we have. So we have two types of bendings. So the first type is that what we had it so far, and it was the pure bending on the moment. So if I have the beam like that, this beam would be bent like this, or smaller. Bend like that. If I just put the moment, if I apply the moment somewhere on that beam, so it's gonna bend. So that's called the pure bending. So that's the pure bending. That's a pure bending, or basically, when we talk about the pure bending, was that no shear forces. So pure bending. But I can get the bending if I, instead of having it like that, if I have the same beam. So if I have the same beam, and this time I'm gonna get the bending if I put a force at the very tip of that. So if I go put the force here, it causes the bending. So it's the bending under the transverse load. So it's going to be bending under transverse force. So there's a transverse force or transverse load that causes the bending. So in this case, we have the shear force. So we have shear force. So in the first case, no shear force, the pure bending, just a moment. In the second one, we have the shear force. So these are the two. So mostly that we are dealing with is going to be this type. So we have some transfer load that causes the bending, and then we are going to look at it, how we are going to deal with that. The next is the types of load that we want to look at is somehow what types of load we have, or basically what types of transverse load we have, so we can work with that. So next is the types of load. So again, if you remember from the statics, we have two types of load. The first one is going to be the concentrated load. So if I have a beam like that, then I would have, for example, two load applying anywhere like that. So these are concentrated loads. Concentrated force. So that's the first type of force that we have. The second type that we had was distributed load. So if I had the same beam, and then I have the types of load applying on that. I assume it's going to be look like this. Gonna have some loading applying on that, like that. So this is gonna be the distributed load. Let's call it the distributed load. Means that you have the load distributed over part of the beam or the entire beam. Remember that the distance between the supports, it's called the span. So span is distance between supports. You will see that. So the distance between the supports we will call the span. So that's the next. So it's the type of the loads. We have the concentrated load and distributed load. The next thing that we want to talk about is the statistically determinate or indeterminate beams. So the beams can be statistically determinate or indeterminate. We're going to look into those two types as well. So the next thing want to look at it is the statistically determinate beam. And the book shows that 3 cases. It's not going to link that to these 3 cases, but just as an example, 3 cases. So a statistically determinate beam. Statically, sorry. So static. Determinate beams. I said the book gives the 3 examples. So the first one that's giving is just this very simple beam that it has 2 supports similar to what we have here. So if I have a beam like that, simple. That's called the simply supported. Simply supported beam. So it's very simple. The second case that we have is that we're hanging beam. So if I have a beam that goes there, I instead of having this next beam at the very end, I have it, for example, somewhere here. Support against, I have this part, that's a simple supporter, and then I have the overhanging part. So it's going to be the overhanging beam. Or when we have one fixed end, another one that we see the lots, that if I have a fixed end at one of the ends, and the beam is going to be like that. So I have a fixed end, and then I have the beam. It's going to cancel everything. Does it? One fixed end. So in all of these cases, what we have is that there are three unknowns. So I can use the statics equilibrium equation, sigma f x0, sigma f y0, sigma m about any point 0, and find the reaction of the supports in either of these three cases. But there might be cases that I have more unknown than I can calculate. So I have three equilibrium equation. If I have 4 unknown or more, then I cannot use simply equilibrium to solve them. And based on the statics, they are indeterminate. So I cannot find the reaction just by using the equilibrium equation. I need the deformation equation about the shapes to solve those problems. So statically indeterminate beam. The next part is again, it gives 3 examples. It's not going to be limited to these 3. You can have many more cases. So the first one is that continuous beam. So if I have the same beam like this, but assume I have one more support somewhere here. So now I have 4 unknowns. So I have 2 unknown here, 1 here, 1 here, 4 unknown. So I cannot solve that. So it's going to be continuous beam. The next one is that if I have a fixed end and a support end other end, so if I have a fixed end here, and then I have a support here. So it's going to be fixed at one end and simply supported at another. So it's fixed at one end, fixed at one end, and simply supported at other, and simply supported at other end. So, makes sense. And then, and so it's again, I have 3 unknown here, 1 unknown here, 4 unknown. So I cannot solve it with that. Or what if I have the both end fixed? So if I have a beam here that has fixed end at both ends. So if I have a beam like that, so it's a fixed beam, close end. So if I have like that, I have 3 unknown here, 3 unknown there. So a total of 6 unknown. Again, it's statically indeterminate. I cannot use only the knowledge of the static to solve either of these 3 examples. And then very last thing that very briefly want to look at is the beams with the hinges. The things about the hinge is that when we have a hinge, let me draw it first. For example, if I have a beam like this, there's a hinge here. And so assume there's a fixed end here. There's a fixed the simple support there. So if you'll look at it here, what I have is that at the first glance, if you look at it, it can have 1 hinge or more than 1 hinge. So I have 3 unknown here, 1 unknown here. I have 4 unknowns in total in that beam. So with the statics, I cannot do anything with that. But I have a hinge, and in the hinge, the beam can move. Okay, the beam can rotate. The nothing prevents the beam from rotating about that hinge. So if nothing preventing it from rotating, it means that the moment about that hinge or at that point should be 0. Because it cannot move here, but here nothing prevented from the rotation. It's a hinge. It's like a hinge, it just can't rotate. Because it can rotate, it means that the M at that point is 0. So basically the internal moment at that point is 0. So we know that the internal moment at the hinge is 0, and it gives us another special internal moment at hinge is 0. That information gives me an additional equation. So I have 3 equilibrium. So I have 3 unknown here, 1 here, 4 unknown. I have 3 equilibrium equation and 4 unknown. So I need this the fourth equation to solve it. And I get the fourth equation for that internal moment at that point should be 0. So basically, if I disassemble it about that point, about the hinge, and write the moment about that hinge, it should become 0. Gives you additional information. So these are basically the very quick review of the beams, and what we have about the beams. And then we will go ahead and start looking at the, okay, if you want to design either of these beams, any of these cases, how you can design. So the next step is that, okay, if you are given any of these cases, how we can design a beam? How we can design that beam? So So first of all, we're gonna to look at the general case how we can design it. So assume I have a beam that is, it's gonna look like this. So it's a beam. Bring it a bit lower so you can put the load on top. So we'll have a beam. And then I have some distributed load, some concentrated load on that beam. So I have, for example, some distributed load from here to here, and then have some forces here, F1, F2, and it's going to be double. So I have a beam look like this, and I want to design that beam. So if I want to design that beam at any point, any location that I'm in, I have to go ahead and find the internal force there. So if I point A, B, and then if I want to design it for section C, I have to go ahead and cut it in that section and see what's happening inside that beam. So if I want to design it to make sure the section C doesn't fail, I have to cut it there and see what's happening there, and then design the beam to make sure it doesn't fail. So if I go ahead and start looking at, so I'm gonna split the beam into two halves. So it's gonna be this part. So from the A to C. And then I have from the C to B. So it's gonna be the A. That's going to be the point C that we break it. It's going to be the C. It's going to be the B. The forces we have the distributed load and F1 on the AC. So we have the distributed load W and the F1 here. And then we have the F2 on the other side. And then we have the internal force. Again, it's the reminder from the statics that we had. So once go ahead and look at the internal force, we know that we have the shear, we have the axial load, and we have the moment. So we have the axial load, and I'll draw the positive direction. So that's going to be the axial load of P. Then I would have shear load that's going to be going down here and going up here. And then I have the moment at C. That's going to look like this. So these are my internal forces, and I want to, okay, make sure that whatever I'm designing at that point C is not gonna fail. So in this case, first we are looking at the, basically we are still dealing with the moment. So I want to make sure that the beam that we are designing doesn't fail about the moment. So if I look at that, I want to make sure that's not failing there. So I have to go and find the sigma. And what was the sigma? The sigma was MC divided by I. If I want to make sure that beam doesn't fail, if I want to make sure that beam does not fail on the bending, I have to go ahead and find the maximum sigma in that beam. So if I want to find the sigma, the maximum sigma in that beam, where the maximum sigma happen, where the moment is maximum, when the internal moment is maximum. So I want to find where the sigma is maximum. I have to go and find where the M in that entire beam become maximum. So here when I cut it at C, I know the moment at C, but is the moment at C is the max? Is the moment at C the maximum? Probably not, probably. It might be, it might not be, I don't know. If I cut a little bit to the right or to the left, or if I cut it here, if I cut it here, I don't know. I need to know where the M is max. When I cut it at C, I only know the moment at the C. So instead, I want to make sure I get that moment, that internal moment, so let me put it just simply M. I want to make sure that moment, the internal moment is max, so I can get the C max. So sigma max occurs where internal moment M is maximum. So the sigma become max when the M become max. So M is the internal moment. So I have to go in that beam and try to find out where that M become max. That's what we are looking for. So again, if I cut it at C, that's the M that I find at C. But is this the max? Maybe yes, maybe not. We have to make sure we know where it is max. So basically the design procedure, so the beam so the design procedure for bending, we want to, okay, if I want to design a beam for the bending, what's the design procedure is that the first step, I have to find the moment diagram in that. So draw moment diagram for the entire beam. Why should I do that? Why should I draw the moment diagram? Because I said I want to know where the M is maximum. So I have to know the moment is the entire beam. So I have to go ahead and calculate the moment for the entire beam from the beginning to the end. And then I have to find the maximum moment. Then next step is that find maximum internal moment M. So the next step is that I have to go ahead and find the maximum internal moment. When I know that where is the M max, so I can work with that. So I have to find the maximum internal moment. The next thing that I have to find is that maximum allowable stress that my material can handle. So if this is a steel, it's going to be different stress I can put on that compared if it was a wood. So I have to find the maximum allowable sigma. So the next thing is that find maximum allowable stress, or basically the sigma allowable. So we want to find the M max, then we want to find the maximum sigma allowable. These two. When we have these two, then I can go ahead and say, okay, then use the bending equation as that. So then we have that the sigma allowable would be equal to M max C divided by I, which is equal to M max divided by S mean. So remember that the S is I divided by C. Then find S mean. So that's the minimum S that we can find. We can find S mean. So that's the minimum S that our cross section can have before breaking, before failure. So we use that, and then we find, so we know the sigma allowable, we know the M max, so we find the S mean, and then later on we'll talk about it. There are the tables. From the beam table we start the cross section. So then use beam table to select the cross section cross section that basically select the section that its S is larger than is that so select section with S. So I want to find the cross section that its S is equal or larger than the beam. And so the some samples of those tables will work with them later on, or at the very back of the book. So have them there. We'll look into them later on. So, or depend on whatever you're designing, there are standards, go there and get them, and there's the tables for steel beam, for wood beam, for different shape of the cross section, so you can use them and find the S that's larger than the minimum S, and you can use that in for use. So that's the design procedure. So we'll work on that. So the next step that we're going to work is that the very first is that we have to learn how to draw the moment diagram for the beam. So the next thing we'll work on that, the first we learn how to draw the moment diagram using the method we learned in the statics. And after that, we'll learn how to use some techniques to draw the moment diagram and the shear diagram more quickly, more efficiently. So that's going to be the next step. So the next step is learn how to draw the moment diagram using the techniques I'm going to tell you, and find the moment, the maximum moment in there. And then we will go through all of this. So by the end of this chapter, we go through all these steps